Hello, my name is Higashino from Z Engineering. For the past 42 years, we have been working with steam traps. During that time, we have seen steam systems in many different factories. This YouTube channel is not meant to defend or promote office traps. Instead, we will talk about the real problem that's actually occur in steam system in the field, and how we have tried to find answers to those problems through our work on site. That is what this channel is about.
In the previous episode, we discussed that steam leakage cannot be quantified simply by measuring condensate volume. Even if we collect condensate for the same 10 minutes, the amount collected changes every time. Sometimes, the difference can reach nearly 20%. So, the question is this: if the collected volume is almost the same, does that mean the steam leakage is also the same? The answer is no. What is actually lost in the field is not steam itself. It is thermal energy. Today, I will explain how steam loss can be estimated in real factories using a method called the condensate collection test. First, let me give the conclusion. ISO testing methods cannot be used in real operating plants. Measuring condensate volume alone cannot determine steam loss. What must be evaluated is thermal energy. There is an ISO method for measuring steam leakage. However, it requires very specific conditions. Only steam is supplied. No condensate is allowed to flow, and the valve is measured in the closed position. In other words, this test measures steam that passes through even though the valve is closed. Under these conditions, a major tire manufacturer conducted a comparison test. The result was clear. The orifice trap showed the maximum flow. In other words, it was evaluated as the worst case for steam leakage. This is not surprising. An orifice is always open. But the situation in real factories is completely different. In real plants, condensate is always present. The trap is not closed. Steam leakage occurs only when the valve opens. What we really need to know is something else: how much steam energy is lost during actual operation. So, how do we measure steam energy loss in the field? The condensate collection test is performed while the heat exchanger is operating. What we measure is mass and temperature. If steam mixes into the condensate, the temperature of the condensate increases. Whenever steam mixes, thermal energy must increase. So the evaluation is not based on volume. It is based on thermal energy. In this test, two traps are compared under the same operating conditions. The difference in thermal energy reveals the steam loss. There is also another important factor: the piping configuration. If the piping layout is not correct, the test cannot work. In fact, I personally failed several times before learning this. The pipe connecting the trap to the collection tank must be as short and straight as possible. If there is reverse slope, condensate accumulates. Accurate collection becomes impossible. There is also one more critical step. Before collection begins, condensate must be discharged externally for 10 minutes. If this step is skipped, the condensate flow does not stabilize, and the data will always be unreliable. Now let me explain the actual procedure. First, a fixed amount of water is placed in the collection tank. For example, 6 liters. The water volume and temperature are recorded. After the 10-minute external discharge, collection begins. Condensate is collected for a fixed time. For example, 10 minutes. After the collection, the water volume and temperature are recorded again. The water is then replaced, and the test is repeated 3 to 5 times. Then the trap is switched, and the same test is performed under identical conditions. The data shown here was measured at a tire factory in Bangkok. Steam at 6 kilograms pressure becomes condensate at about 165 degrees Celsius. However, the temperature measured in the tank was 137.3 degrees. This means a large amount of heat energy was already lost from the piping before the condensate reached the tank. Therefore, if we compare the data without correction, the evaluation is not accurate. So we correct for the thermal energy lost in the piping. After applying this correction, the comparison becomes clear. The TS0 trap shows almost zero steam leakage. The TLV trap shows approximately 8%. The key point here is very important. We are not comparing condensate volume. Condensate flow changes significantly. Even within the same 10-minute period, it can vary by 20%. But when steam mixes into condensate, the temperature always increases. So when we evaluate thermal energy, the difference becomes clear. That difference represents steam leakage. Let me summarize today's conclusion. In real factories, condensate volume changes constantly. Therefore, comparing volume alone cannot determine steam leakage. What must be evaluated is thermal energy. In the next episode, I will discuss a problem that many steam engineers struggle with: two-phase flow. Why condensate behavior is so difficult to predict in real systems, and why engineers often cannot calculate it accurately.